Okay, the title of my talk summarizes quite well what I'm going to describe, which is a powerful method for the calculation of the thermal load-induced notch stress intensity factors by using the strain energy concept. I have divided my presentation in 4 steps. After a short introduction, I will describe the analytical frame, which are the equation at the basis of such a methodology. In the first step, I will describe a case study, and finally the conclusion as well. Okay, we are talking about notch component, sharply notch component. And we all know that in such a geometry, the stress distribution near the notch tip are singular. That means that are asymptotic. And the solution was first obtained by William several years ago. And what is important is that the intensity of such stress distributions are quantified by the notch stress intensity factors, which is a parameter which is already used in literature for the assessment of the static and dynamic and fatigue strength of notch component. And this is also true in the case of thermal loads. In fact, such parameter, for example, in the case of thermal load, can be used to assess the thermal fatigue strength of a notch component. Example coming from electronic device. Which is the analytical frame of the methodologies. What's my goal? The goal of this presentation is to present a new method for the calculation of such local parameters. In the past, and I say the classical methodology for the calculation of the notch stress intensity factors, or thermal and SIF, is based on Gross and Mendelssohn definition. The main drawback of such definitions is that one has to calculate the stress distribution using a very fine mesh. A high density, a mesh with a very high density of nodes and elements, because this high density mesh is necessary in order to obtain the asymptotic distribution, to capture the singular behavior, of the stress distributions. We remember that in 2001, Professor Lazzarini and Professor Roberto and co-workers have formulated a new parameter, a new field parameters based on the strain energy density average over control volume. This is the expression of such parameter. Such parameter is used in order to quantify the static and fatigue strength of notch components. But it is not my goal to deal with such energetic criterion because it just described in literature. What I want to highlight is that by using a reverse formula of the strain energy density, average over the control volume, it is possible to obtain a new formulation of the strain of the notch stress intensity factors, which in turn depends on the numerical values of the strain energy density. This is a great idea because the strain energy density depends only on the nodal displacement and the Stephen matrix of the elements. What does it mean? It means that the strain energy density do not depend or is almost independent of the mesh density, because the displacements are almost independent of the mesh density. This is also true for the thermomechanical computation, because the displacement in thermomechanical computation are related to the variation of temperature at nodes. And the temperature works like the displacement. I mean that also the temperature at nodes are almost mesh independent. So one can calculate the strain energy density using a coarse mesh, not a very fine mesh, a coarse mesh, and then use the reverse formula, obtaining the value of the notch stress intensity factors. This is the methodology. In order to demonstrate that this method works, we have simulated a simple geometry like this, because we know the analytical temperature distribution, which is quite similar to the Williams solution, because we have eigenfunction, eigenvalues, eigenvalues. The only difference is that the thermal distribution near the notch tip is not singular. The temperature distribution is not singular, conversely to the stress distribution. The thermal load were applied in terms of a symmetric heat flux on the external surface of the geometry and the antisymmetric heat flux in order to divide the mode 1 and mode 2. This table summarizes the material properties using the simulation, which mesh the property of carbon steel. This slide summarizes the results obtained after the thermal simulation. This plot is the temperature distribution along the notch bisector, and we can observe first that the solution is in agreement with the analytical values. But what is most important is that the temperature distribution is almost mesh independent. The continuous line is the temperature distribution contained with the finest mesh at the top of this table, while the circles are the solution of the nodal temperature obtained with the coarse mesh at the bottom, of this table. We have the same values, the same distribution of the temperature. That means that it means that the temperature is almost mesh independent. The temperature at nodes. Now, if we apply such temperature distribution in order as a load for the calculation of stress distribution, we obtain this plot. Mode 1 shows a singularity, which in a log-log plot is represented by the straight line. Mode 2 is not singular, but it is not important, this result. We know the result is expected. What is important is that if we calculate the strain energy density by varying the mesh density, we obtain almost the same values, with an error which is in between 1.7, 3.5%. And therefore, if we calculate the notch stress intensity factor induced by the thermal load by using such values of the strain energy density, we obtain obviously a similar value. So, the conclusion. We have demonstrated that there is the possibility to calculate the thermoelastic stress intensity factor by using the strain energy density concept. This is very strong, this is very powerful method because the strain energy density does not depend on the mesh. And one can also, what we can do is calculate the strain energy density by using a coarser mesh and then to obtain the correct values of the notch stress intensity factors. There is a limit, in my opinion. This approach doesn't work in the case of cyclic elastoplastic loading because in this case the strain energy density accumulates during the thermomechanical story of the notch component. I conclude my presentation. Thank you very much for your attention.